Hi everyone, have you ever wondered how the microchips in your phone actually work? Or why power lines don't melt when they're carrying really big currents? It's all down to resistivity. This is a property of materials that controls how easily electricity can flow. In this video we'll break down what resistivity is, the key formula you need for your exams, and why it's so important in electronics, semiconductors, and also in power systems. I hope you enjoy the video. So resistivity. If we think about a wire, copper wire, any wire which conducts electricity, the resistance of the wire depends on three things. It depends on the length of the wire, the material of the wire, which as we'll see is related to resistivity, and also the cross-sectional area. So we've already talked about length and cross-sectional area in an earlier lesson, so now we're going to consider the material that the wire is made of. So the symbol we use is this rho curly P, called resistivity. The units are ohm meters, not ohms per meter, ohm meters. And if we go back to this idea here, the resistance we already know is related to the length. The bigger the length, the bigger the resistance. That's proportional. We already know that if we increase the area, then the resistance decreases. So that's an inverse proportional relationship. So we've already considered these ideas here. And the resistivity is effectively the constant of proportionality in this relationship. So the resistance is equal to resistivity multiplied by L divided by A. Alternatively, if you make rho the subject, so rearrange this formula, rho is equal to RA over L, and then we can work out the units because we have ohms times by meters squared divided by meters. Meters squared divided by meters gives us meters, ohm meters. We need to know the definition, and the definition is based on this relationship here. So the resistivity is equal to the resistance per unit length, R over L, if we have unit cross-sectional area, or a cross-sectional area of 1 meter squared. So that's our standard definition, the resistance per unit length of a material with a cross-sectional area of 1 meter squared. Alternatively, we could say the resistance of unit volume, because if we have 1 meter squared and unit length, we have a volume of 1 meter squared times by 1, which is 1 meter cubed, which is a cubic meter of the material. Be careful though, it's not resistance per unit volume, that will be incorrect. It's resistance of unit volume. We're not expected to know the values, but it's useful to have an idea of what they are. So we know that copper is a good conductor. Resistivity values are really quite tiny, so 1.72 10 to the minus 8. Silver is actually a better conductor than copper, 1.64 10 to the minus 8. But obviously silver is more expensive and it's a rare material, so we tend not to have wires made of silver. And nichrome, you may have come across this before, that is sometimes called a resistance wire. It has a relatively high resistance, and as we can see here, it's significantly higher than copper and silver. But expect a value of resistivity 10 to the minus 8. That's a fairly typical value of resistivity. Okay, we're going to go through a worked example. If you want to, you can pause the video and have a go at this yourself. What we find is, the first thing we usually have to do is to find the cross-sectional area. So we've got a diameter of 2.5 millimeters. Be careful here, we're normally given the diameter, so we need to divide by 2 to get the radius. We also need to convert millimeters into meters, 10 to the minus 3. So these two stages are very often missed out by students in the exam. Change into meters, divide by 2 to get the radius, and then square it and then times by pi. So in this case we get 4.9 10 to the minus 6, so really quite a small value. If we're talking about wires of a millimeter or half a millimeter, something like that, we would expect an area of 10 to the minus 6, 10 to the minus 7, maybe even 10 to the minus 8. If you're getting a cross-sectional area of 0.5 or 0.06, you've probably made a mistake, or you're looking at a very, very large component indeed. Okay, so we're trying to find the resistance, so we have our formula. We need to make R the subject. R is equal to rho L over A. So we know rho, we're given this value. We're normally given this in the formula in the question. Multiplied by length, divided by our area in meters squared, and we get a value of 0.01. So if we're talking about copper and we've got a reasonably large diameter and only a few meters, expect a small value. So 0.5 ohms, 0.06 ohms, something like that. If you get a very large value, you may have made a mistake. Okay, so now it's your turn to try some questions. So have a read of the questions, pause the video, and then when you've had a go, you can have a look at the answers. Question 1, explain the difference between resistance and resistivity. They both sound quite similar. They are related, but they are different quantities, different values. The best way to explain the difference is just to write out the definition. This is a very typical exam question. So rather than say, well, one's to do with the material and one's to do with the properties, or depending on the voltage, you're getting a bit of a muddle. Just give the definition. So we've defined resistance as the ratio of V to I, and we've just defined resistivity as the resistance per unit length, or ratio of resistance to length, for unit cross-sectional area. So that's the best way to avoid getting in a muddle. Question 2 is a standard exam question. There you may get asked to work out the cross-sectional area, as in this case. Watch out for millimeters and diameter, so we need to divide by 2 and divide by 1,000. And then pi r squared, we've got this tiny number, 5.5 10 to the minus 7, sounds about right. The resistance, we can rearrange this expression here to make r the subject. We've got the resistivity, we've got the length, and we've got our value for cross-sectional area. 0.69 ohms, sounds about right. So exam tip, standard form, obviously show you're working, convert to meters, and expect a small value for the cross-sectional area, typically. Question 3 is another fairly typical exam question. So we're told a value is 36 ohms for a particular material. This idea of relationship, so what happens if we double the length or halve the area, etc., is a really common question across all the exam boards. So if we have the same area but double the length, then it's going to be double the resistance. So we can see the relationship between resistance and the length, it's proportional. So if we double the length, we double the resistance. If we keep the length the same but double the area, well, we said there's an inverse proportional relationship between resistance and area. So if it's twice the area, it's going to be half the resistance. Therefore, it's going to be 36 divided by 2. If we double the length and half the area, so double the length is going to be twice the resistance. If we half the area, we're not halving the resistance, we're making it smaller, it's more difficult for the electrons to pass. It's inversely proportional, so half the area is twice the resistance, so we have times 2 and times 2, total times 4, which will give us 144. And then finally, if we half the diameter, well, it's pi r squared, so half the diameter is going to be a quarter the area, it's a squared relationship, but we're dividing by a quarter, which gives us multiplied by 4, which is 144. Okay, question 4, another typical question. It's just a variation on question 2. So I've done all the calculations together here. You might want to do that if you're feeling confident with your calculator technique, but you may just want to calculate the cross-sectional area separately. Don't forget, divide by 1,000, divide by 2, pi r squared, and then substitute, and we get a value of 91.8. Right, it's time to review the key ideas from this lesson. Have a read through those questions, pause the video, you might want to write these down or just think these through in your head, and then when you're ready for the answers, press play. Right, so resistance we've defined previously in an earlier lesson, the ratio of voltage to current. Very important. We said there are 2 definitions of resistivity. The standard one, the resistance per unit length for unit cross-sectional area. Alternatively, the resistance of unit volume. Be careful, not per unit volume, of unit volume. The units are ohm meters, and we can show where they come from with the formula. And then, typical question, we've got these kind of relationships. What happens if length and diameter are changed? If we halve the length, well, it's a proportional relationship between R and L, so we halve the resistance. If we halve the diameter, well, pi r squared, that means we're going to divide the area by 4, but that's an inverse proportional relationship between R and A. So if we're dividing by a quarter, that is multiplying the resistance by 4. So divide by 2 and multiply by 4. The overall effect would be multiply by 2. There should be a Kahoot quiz in the link below the video if you want to review some of these ideas.